Now, in the last class, we have gone through the change of direction in the linear element. First, we have started in this chapter of strain analysis the position of a particular point as per the rectangular coordinate axis, and how it is changing with the force or the external application of certain type of forces. Next, what will be the coordinates of the final position. Next, we went through a straight line whose initial coordinates are known and final coordinates are we have to calculate. And this straight line, after the deformation, how its coordinates are changing and what is the value of its coordinates itself. Next, we went through the what are the change in direction of the linear elements itself. First, we have to change the position. Next, we have to discuss with the direction of the change in the direction with the external application of some other external force over a certain mass of a body, whose related elements we know, and we know the position of the straight lines, which is at an angle with each other, and next, how it is changing with the application of external loads. Next, we have to consider today a term known as cubical dilatation. This means, say, we have a cube or a parallelepiped, means sides are parallel, corresponding or opposite sides are parallel to each other, which is parallelepiped. And due to the deformation, due to the external application of force, this parallelepiped is deforming. And how does its different points are available. Now, next, let us consider a point A with coordinates is given in rectangular coordinate system with x, y, and z, and a neighboring point B with say coordinates is given as x plus delta x and x plus delta x, y plus delta y, z plus delta z, etc. So, along the x-axis, we know the distance from origin to x-axis, origin along the x-axis of the point A, and we know same distance of the point B along x-axis, which is slightly more, is x plus delta x, but infinitesimally small, but not equal. Same is the case with y-axis, same is the case with the z-axis. All the coordinates are changing by an infinitesimal amount. Because all this equation, you cannot change more because deformation is too excessive, that you cannot take into account in any of these equations. So we are always assuming that it changes differential, changes infinitesimally small or elemental change. Now, after the deformation, the point and B, A and B moves like this. Say initially the point A was x, y, z, and B was x plus delta x, y plus delta x, and z plus delta x. Say after the deformation, x becomes x plus ux, y plus uy, z plus uj, and B dash becomes, which is the final position of the angle point B, x plus delta x plus ux plus delta ux, y plus delta y plus ux plus delta uy, z plus delta z plus ux plus delta uj. This we have discussed how it is coming in this equation. I'm just telling you very briefly. Initially, the coordinates are changed. Coordinates A, position of the coordinates A was changed to the position of the coordinates A dash, and so it is changing by the displacement vector A dash, and the changing by the direction cosines of the displacement vectors A dash, means A is a straight line if it has its cosines along x direction, y direction, and z direction is defined as the direction cosine of the AB of the line A dash. The direction cosines are given as ux, uy, and uz respectively along x, y, and z axis. Similarly, the point P, whose initial coordinates was x plus delta x, y plus delta x, and z plus delta y, z plus delta z, is now changing to x plus delta x, ux plus delta ux means how much this direction cosine from ux to changing in x direction due to its change its position. It is not saying that it did not change its position, it remains b. No, it is not that. It is changes infinitesimally but changes. In along x direction, with x plus delta x, which was the original position, it changed to u plus x plus ux plus delta ux. Delta ux is the rate of change of the direction cosine along x-axis. Similarly, y plus dy, y plus dy is the direction cosine, y plus delta y plus uy plus delta uy is the rate of change of direction cosine along y-axis. And similarly, z plus delta z plus uz plus delta z is the rate of change of direction cosine along the z-axis itself. Now we know ux, uy, uz are the components of displacement of point A. So from that initial point, we know delta ux is the rate of change of ux. It is given here. The rate of change of delta ux in terms of delta x, and as the delta x is changed by delta x, so rate of change will be multiplied. This rate of change multiplied by the value delta x. Similarly, rate of change of ux in terms of against y is the change in y. As the y has changed to delta y, so the multiplication of these two items will give you the change. And delta rate of delta x in z direction in terms of z multiplied by the original change in delta j. So, and if you add together, you'll get the total change of delta ux. Similarly, we have the total change of delta uy, and we are having the total change of delta uz itself. Now, the x-axis, the displacement segment a dash b dash will have the following components along x, y, and z axis. What is that? In delta x, x-axis it becomes x delta x plus delta ux. So we have to put the value of delta ux from this equation here. So it will become 1 plus delta ux by delta x plus delta x, and delta x by delta y into delta x remains same, and delta ux by delta z into remains same as it is. That is ours. The y-axis, the displacement of the segment y b dash of the following components in z-axis. Y-axis we have this component means delta y plus delta uy, and delta uy by delta x into delta x 1 plus delta uy plus dy into delta y, because we are adding delta y here. So delta y, if we add with here, it will become 1 plus dy by del uy by dy into delta y plus delta uz by delta z into delta z plus next z axis delta delta z plus delta uz is equal to delta uz plus delta ux into delta x plus delta uz plus delta y to delta y plus 1 plus delta uz plus delta z to delta z, because here along z axis we have this change here, have this change. If we add, then it will become 1 plus like this. If we add this with this delta z will come out will be 1 plus dz by dz itself. Just 1 second. Let us get to the next page. Is 14. Now here we are considering I have told you in the beginning that we are supposed to calculate what is the deformation of a parallelepiped or rectangular height, rectangular mass, rectangular block. What we hear is infinitesimally rectangular parallelepiped. What is meant by parallelepiped? You know, a parallelepiped is the cube whose sides are all parallel, or may not be equal or may be equal, but sides are parallel to each other, corresponding sides. You know, this side is parallel to this side, this side is parallel to this side, and this side is parallel to this side. This is defined as parallelepiped, and we call it is an we are saying that is an infinitesimally rectangular parallelepiped. Why is it called rectangular? All the individual in between angles are equal to 90 degrees. All are vertical with each other. So it is called rectangular parallelepiped. First, infinitesimal, all their sides are infinitesimally small but not zero. It tends to zero but not zero. Rectangular, all the sides are perpendicular to each other. Parallelepipeds, they are all the planes are parallel, corresponding planes, not each of them, but corresponding, like this one with this one, this one with this one, and this one with this one. This is parallelepiped. So this type of parallelepiped, what we have here, the sides have delta x, delta y, delta z. These are the sides. So you know, from the starting of the point P may have a coordinate x. So from here the sides are increased. Delta this side q may be equal to delta p x plus delta y, and this that is s may be x plus delta z plus delta z, and r may be y plus delta r, and q may be x plus delta x itself. Now what happens here, under the action of such external forces, the body with whose part is this cube or parallelepiped is deformed, and as a result this parallelepiped is also deformed to a certain extent, and it takes this position p dash, q dash, s dash, r dash, etc. But this deformation is also infinitesimally small but not equal to zero. Now what is how we can identify? Let us have PQ with AB. Equation number 28 means where delta y here above the line PQ, on any point above the line PQ, unless it reached here, there is no change in delta y or delta z. So delta y and delta z over the line PQ, which takes the position P dash, Q dash, etc., is equal to delta y and delta z. So the equation I've just told you just at this moment is all these delta y, delta z will become 0. Y-axis, along y-axis will be 1 plus delta y by delta x into delta x. Along x-axis, along y-axis it becomes delta y plus delta z, and along z-axis this becomes this equation itself. Delta y, delta z 0, delta z. So I'm just opening that equation again. It will be clear to you within moments. Just show the 14. Here is the equation. Just have explained that. Here we know there is no change in the direction delta y, no change in the direction delta z. So all these right-hand terms are equal to 0. Only delta x have value because we are considering the change or along x-axis, y-axis, and z-axis. So delta x change of ux, or change in your direction cosine along x-axis becomes this form. All these others are equal to 0. So this plus delta x, and this will be only remain this portion, and for uz only this portion will remain as it is, and other terms are as delta y, delta z is 0. All these 6 terms are equal to 0 itself. Hence, we can successfully identify AB with PQ, where successfully identify AB with PQ, where delta y delta z is equal to 0, means there is no coordinate is not changing. Delta y coordinate along y axis and along z axis there is no change. With PQ only x axis the change is there. So we can successfully identify AB with PQ. We can successfully identify PR. We see it is given here. AB with PQ. We can also identify PR here and identify PQ here like this, where account PR delta x, no coordinate change in delta x, no coordinate change in delta z, and along PS no coordinate changing in along x-axis and no coordinate changing along y-axis. Both delta x delta y is equal to 0, and got the component P dash Q dash. Thus, this time here PQ was there, now it's changed to P dash Q dash. So for a change in from here to here, the parallelepiped has changed, but its length, there is only change along the change in PQ will be only along P dash Q dash, and similarly for the others. Let us see. So along x-axis the component x P dash Q dash, P dash R dash, and P dash S dash along x, y, and z axis. So what will be that? It will be x-axis 1 plus delta u by delta x and delta into delta x, PR delta u by delta y, pz delta u by delta u by delta z delta x. Similarly, delta y plus delta x into delta x, 1 plus delta u by delta y into delta y, and 1 delta u y by delta z into delta z. Similarly, delta z is delta uz here by delta x into delta x, and delta uz here by delta y into delta y, and 1 plus delta uz by delta y into delta z. So we have a matrix, deformation matrix. The volume of the right parallelepiped before the deformation is equal to, we know before the deformation, the volume of the right perpendicular pipette before the deformation equal to V into delta x into delta y into delta z. How? It is like this here. The coordinates of Q is, for x coordinate of Q is x plus delta x, y coordinates of Q is R here, x y plus delta z, y plus delta y, and z coordinates is P into PS is equal to z plus delta z. So PQ is equal to delta x, PR is equal to delta y, and PS is equal to delta z. So it's the volume of this cube will be delta x plus into delta y multiplied by delta z itself. That is the idea. So before deformation, we got the volume delta x plus delta y into delta z. The volume of the deformed after the deformed parallelepiped is obtained from the well-known formula of analytical geometry. I am telling you. 15, 16. So volume will be equal to, final volume will be equal to V dash, V plus delta V, which is equal to T multiplied by the original volume, delta x, delta y, delta z. What is D is that the following determinant or following matrix. Just we have shown it there, how it is created. This is the determinant itself. So final volume D dash is the multiplication of the determinant D with the initial volume of the parallelepiped itself. So what we have done here, we have just calculated the change in the individual angle due to the change in volume, change in the individual side due to change in volume, and we have made a matrix with this newly defined changes, and this matrix we are defining as the D determinant D. Thus, it is assumed that the strain in one quantity strain, all the strains are small, such that the squares and products can be neglected. So, what if we can have the product dux dy is square, or if you multiply dux into dy, etc., all these things are extremely small, all can be neglected. So, what is left is equal to, if you make this matrix integration, you will find that only this portion exists, that is 1 plus del ux del by dx del uy by dj plus del uz plus dz. So 1 plus epsa xx epsa yy epsa zz, or the change in strain along x-axis, change in strain along y-axis, and change in strain along z-axis. We know change in strain along x-axis will be the rate of change of direction cosine of x, direction cosine along x-axis, and change in strain along y-axis is very clearly direction cosine of change in direction cosine with del y-axis, and change in uh, change in the change in strain, or the strain existing along z-axis, the change in direction cosine along z-axis itself. So d, or the determinant, becomes 1 plus epsa xx plus epsa yy plus epsa zz. Hence the new volume according to the linear strain theory will be delta v dash delta v plus delta v, or equal to 1 plus, which is where d and delta v is given as 1 plus d and delta d is given as this formula, this d multiplied by delta x y z, delta x delta y into delta z is equal to 1 plus epsa xx plus epsa yy plus epsa zz multiplied by delta x into delta y into delta z itself. This is the final volume, or initial from the, which change in final volume from the initial volume. So the volumetric strain is given by rate of change of volume divided by the original volume, or if you divide, it will become epsa xs, epsa yy, and epsa zz. So what happened? Therefore, so let us go through. According to the linear theory, the volumetric strain known as cubical dilation is also defined as cubical dilatation is equal to the sum of three linear strain along x-axis, along y-axis, and along z-axis itself. Now, let us go through one problem, how you can solve it. Let us see. Now, the following state of strain exists at the point E, Y, Z is given by 02 minus 04, minus 04, 0, minus 04, plus 06, minus 02, and 0 minus 02 into 0, which is given as this determinant D itself. Now, what will be the epsa PQ? What will be the epsa PQ? From the equation 32, we know. From equation 19, it is going on like this. Equation 19 is given as gamma xy uh, actually it is not equation 19 but equation 20. It is given as a, we want to know what will be the following state of strain. So in the direction PQ, having direction cosines equal to nx, ny, so 0.6, ny is equal to 0, and nz is equal to z, and determine the reaction cosine along x-axis, determine the elongation along PQ direction. Now, what is EPQ? EPQ is equal to EXX, that is development of line. Question of line I did not open. H. This is the equation we have produced. E double x, eccentricity along x-axis, multiplied by nx to the power ns square, eyy, ny square, nz, e double z, nz square, plus exy, nx into ny, ezi, ny into nz, and ezx is equal to nz into nx into nz. So what we find here, nx square, which given as nx is given as 0.6, so nx square is equal to given as nx square is given as 0.06, 0.36, and what is ex? Ex is given as 0.02, exx is 0.02. Let us go through. And another thing is, let us stop. Just 1 second, please. Here we have this equation. Here our vector where matrix is given like this, where Exx, gamma xy, gamma zy, as per our numerical terms used here, Exs is here equal to E double x is here 0.02. Gamma xy is given as minus 0.04 and gamma xz is equal to 0. And gamma xy is equal to gamma xy is given as minus 0.04, gamma yy is 0.06, and gamma yz is equal to minus 0.02, and gamma zy is given in our problem is equal to 0, and gamma yz is equal to minus 0.2, and gamma zz is equal to only 0. So that we can go to the equation once again, stopping this relation 16. So we have this equation, and nx square is given as nxs, ny, and nz square is given as here. So if we put this respective value of 0 to as exsy from here and multiplied by 3036, and 066 is here eyy, and it is nyy is equal to 0, so it is 0, and ezz, epsa zz is equal to 0 here, where epsa x square nz square is 64 by 0.064, and putting this value, other values accordingly, we have got this equation of EPQ, or the change in volume is equal to 0.0077 itself. Again, except on this, what is the cubical relation at point P? We know the cubical relation, dilatation means here The volumetric strain is also defined as cubical dilatation. So this is the volumetric strain we want to know, and this is given as Ex, Ey, and Ez, where Ex is given as 0.2, Ey is given as 0.6, and Ezz is given as 0. So this is equal to 0.08. Let us keep the next position a bit. 17. 17. Now, we have gone through the change in the volume. What is the change in volume in terms of deformation itself? Well, the original volume was there. This was a parallelepiped. After the activation of the load, that parallelepiped takes a new form, and we go through what is the change in the volume itself. Now let us go through what is the change in angle between two line elements. What is the change in angle? What we have here, a rectangle coordinate axis system, Ox, Y, Oz, and the straight lines PQ, PR, and that PQ is a line element with direction cosine is given as nx1, nx, ny1, nyz. I am repeating again. nx1 means the cosine of this line line PQ along x-axis. ny1, I am repeating again, is the cosine of this line PQ along y-axis. And nz1 is the cosine of the line nz1 along z-axis. That PR be another element with direction cosine equal to nx2, ny2, nz2. Logic is very clear. Same logic. What is nx2, what is ny2, ny2 is same as nx1, nxy, and nx2 itself, nz1 itself. And theta is the angle between the two line elements before the deformation. This is the angle between the two line elements, and we want to know what will be the change in this angle itself if there is any deformation or due to the application of external force in between these two straight line, which is intended angle equal to theta. Now, after the deformation, we see PQ is become P dash Q dash, and PR becomes P dash R dash with included angle from theta to change to P dash R dash. Now, from analytical geometry, we can determine theta R dash easily from the result of the multiplication of and addition of the corresponding direction cosine itself. So, what is nx1 is the direction cosine of PQ along y-axis 1x, what is multiplied by the direction cosine of PQ along of PR along x-axis itself. So these are the cos of the angle between x-axis and PQ, and this is the cosine of the angle between x-axis and the PR. Similarly, if and you have to add it with ny1 dash plus ny2 dash, which is nothing but the cosine of ny, which is the cosine of ny dash and ny1 dash and ny2 dash. Similarly, nz1 dash and nz2 dash. So what is have here? The cos theta. After changing, initially it was theta. It is changed to the value theta, theta dash, and theta dash is the individual change in the direction cosines of the straight lines whose intended angle is equal to theta dash, where initially it was nx1 dash, nx1, and it becomes now nx1 dash. Initially this was nx2, it become nx2 dash. It has become ny dash and n1y, ny1 is ny2, this becomes ny dash and ny dash. It is all changing accordingly as it is original position from PQ has changed to P dash Q dash, so all the direction cosines are supposed to be changed. Now, from geometrical geometry, you see that the in between angle will be the summation of the product of individual direction cosine itself in the new position itself. Now we have to calculate the value of nx dash, ny dash, nz dash, nz dash, all these values nx1 from the equation 27 itself. In equation 27, we have defined the value equal to of the individual value of nx dash, ny dash, and ny dash we have calculated, and we have let us put it there, and we get this multiplication of such a big amount of multiplications is there. It will take this particular shape with x-axis, y-axis, z-axis, and xy axis, y-axis, z-axis. If the two line segments PR are at right angles to each other, what will happen? Then before strain, after the strain, this equation will become this term 1 into n1 into x1 will vanishes, because when they are at right angle to each other, either x-axis, there is x-axis is not available, and when they are at x cosine is not available, and when they are at y cosine is not available here, and z cosine will not available here. So this will become 2xy, 2xx, 2x1, x2, 2yy, y1, y2, and 2zz, z1, z2. And this gamma 1 also reveals in the same way. All these terms 1 here multiplied by this is vanishes, and it is making a right initial, it was the right angle itself. Now 90 degree minus theta represent the 90 degree minus theta represent the change in the initial right angle. If that is denoted by alpha, then x is equal to theta dash will be 90 minus x itself. Go for 15, 17. Go for 17. 18 there. Or cos is equal to cos theta dash to cos 90 degree minus alpha sin alpha more or less equal to alpha. Since alpha is extremely small, so this equation 36a gives that shear strain alpha between P and Q. If a representation of PQ and PR at P by x dash or y axis, then x gamma x